Okay, welcome to CE 467, Geotechnical Engineering Design 1, lecture number 2. This lecture we will talk about in situ soil properties characterizations. The learning objectives for this lecture is for the students to acquire basic understanding of standard penetration test, SPT, and cone penetration test, CPT, the two very popular field testing for soil properties characterizations in geotechnical engineering. So we talk about how to obtain the field data, and the next step is how to convert those SPT and CPT data into basic soil properties, such as unit weights, soil strength parameters of friction angles, and undrained shear strength. So those parameters will be needed for foundation designs. References for this lecture. So for your textbook, this topic is relevant to chapter 4.3 and chapter 4.4 for your textbook. And there's also a very good YouTube lecture available, produced by UC Davis. He talk about all the field testing. So pretty much like focus on the drilling and the samplings, like a process, which is very good. So give you a chance to have a field experience by watching the YouTube clip. And also, I provide more than enough reference for this class. So if you want to have more details, more like an in-depth understanding about this topic, there's many different like material being freely available online, or you will find it on Canvas. So, what is geotechnical subsurface explorations? So, geotechnical engineers is responsible for acquiring and also interpreting soil, rock, and foundation data for design and constructions of many different types of structures. The proper excavations of this role requires a thorough understanding of the principles and practice of geotechnical engineering, and very important, the subsurface investigation techniques and principle, which is about this lecture, and also design procedure, such as like design foundations that we will learn in this class, and also construction methods, and also plan the facility, um, utilizations of supply that with a working knowledge of geology and hydrology. So pretty much like this is the main scope of geotechnical engineering work, and very important. That's like a very important part of it within it is the geotechnical subsurface explorations, which means we need to understand the investigations techniques and principles that we are about we will use for to get the data that we need. So pretty much like we want to look into the ground with a much better method than just putting our head into the ground. So that's in fact through the developments of the geotechnical engineering, there's many different type of testing method, in situ testing method available nowadays. Um, there's two main categories. One type is what we call the destructive or intrusive testing method, which means like we kind of like penetrate into the ground by some means, either like by a cone like the CPT, like this one. So pretty much like we try to push in a cone into the ground, and then we on the way the cone advance into the ground, you measure the resistance, and then we use that measurements of resistance to correlate with the parameters that we want to find out. And another very popular one that we also talk about is the SPT, the standard penetrations testing method, which is used kind of the principle is very simple. We use a hammer, try to push or advance like um, a tube into the ground, and the tube there will be cables to collect soil samples. And by using like a hammers, we keep counting how many blows that we advance the tubes into the ground, and then we use that blow count. So we have like a blow count over here we call SPT and values, and we use this blow counts to correlate with different type of soil properties that we want to find out, such as like a soil density or soil strength parameters. Uh, so in this class, we will focus on these two testing methods, SPT and CPT. And in fact, there's many different kinds. So we talk about we are both the SPT and CPTs belongs to the destructive or intrusive type of field testing. And there's also more advanced testing, which is non-destructive, which means you don't need to disturb your soil profile. We use like a shear wave velocity, something like a shear wave velocity or a primary wave velocities. Those are geophysical method um, by correlating the geophysical parameters with the soil properties that we want to find out. So this will be much more advanced. So for sure, this will be at graduate level if you want to learn more about those non-destructive type of testing method. You either need to go to grad school or maybe do some research project that will try to advance this type of technology. So this is still ongoing geophysics developments, like there's still a lot of like new technologies going on trying to advance this uh, territories of geotechnical engineering. Um, SPT is very developed already. It's the very original field testing method. So we have a lot of literature and also well documented data. Actually, the most abundance like data available in our geotechnical world is from SPT, particularly in United States. And CPT is the developments of technology or developments of procedure after the SPT. It's relatively new compared to SPT, but it's not like as new as like those non-destructive method that existing or still like ongoing being developed. So CPT come in between. So but we at this point like of engineering practice, we are still trying to perfect this type of testing method. And on Canvex, I upload a YouTube lecture on just talk about CPT. So you may want to take a look. So when you compare SPT and CPT, you need to, if you need to choose one, which one to use, there will be like many questions you need to be answered, like like your budget or like what kind of like a depth you need to go into, and so forth and so on. So hopefully, like reading a textbook and also those like resources available on Canvex, we will help you to understand more about SPT and CPT. And when you go to practice or like as engineers, then you will need to make a choice which method you would like to use for a project. That will be rare that you have a project uh, that allows you to have both of them. Maybe if you work with a mega size of project, that's like a budget is not as much as a constraint as a smaller project, then you may have the chance to do both. But many times you need to pick one, SPT and CPT, and which one to choose will be down to your uh, the restraint of the project, your budget, and many different things. And very importantly, and also depends on your understanding on the testing method, and you will find one that work best for your project. And for the design cost for this one, you're required to this cost 467. You'll be required to do a semester project, and I will give you both SPT and CPT data, and part of the semester project for you to design which in situ test method you will choose for your design project, SPT or CPT. So this is the overview on like those testing method. Uh, this class we only able to cover two, but like on your down your career developments, then you may pick up like a more method based on uh, you know, uh, the career path that you have chosen. Especially if you will work as geotechnical engineers. So after we have the field data, then the next thing is to convert the field data into documentations of the subsurface ground information. So, and what we like, to well, the documentations that we used to document that, we call them to the boring logs. So this will be an examples of the boring logs. After we have those informations, then like through different depth, we can find out uh, the soil classifications. So pretty much this is the soil classifications. Remember, like 366, we talk about the USGS, the classification system, unified soil classification systems. So this pretty much like is telling you what type of soil is it from a depth of 30 feet to 39, for examples. And each boring logs may be come up with a legend. So it highly depends on the project you're working on. For this particular boring logs, so this like a coloring or the symbol here means like a SP materials. So this is a sand type of materials. And we treat those informations from the field testing, particularly for this one, is from SPT, because it gives you the able the samplings that you have from retrieving the soil samples. Then you can do the classifications, and this one classification is classified as SP materials, and the boring logs and also give you more details descriptions of your soils. So soil boring logs give you one locations where you bring the drill rigs to sites to do your SPT or CPT. You core samples or you push the cone and then you get the information you need. Then you convert that back to uh, either soil classifications or we talk more a bit later on how to convert the SPT data or CPT data to our engineering parameters that we need, like a density or soil strength parameters. So if we have enough boring logs, then we can put the informations together to get even more meaningful descriptions of your job site. For example, like this one, like I saw profiles of your project. So this is from the Metro project. So this is one of the bidding documents, geotechnical baseline report for one of the Purple Line stations. And as you can see, pretty much like this is the area that they have done the geotechnical explorations like a program, and then like this part is the how the subsurface the ground subsurface look like. So they have done enough like boring logs. So for example, so maybe this is the first boring logs, and this is the second boring logs, and this is the third like a boring log. So those boring logs was obtained from informations either from SPT or CPT testing. So after you compile all the informations, then you can start connect the docs, and then you can depict the subsurface or try to map what the soil type underneath the ground. Uh, for these examples, this is like a very specific way that the metro projects they use. So the yellow color here for them is just the sand materials. Sorry, and the the green is represented clay. So you can tell the underneath the ground, like what type of material you're expecting. And this is the metro purple line. So this is your tunnel alignments, and this part is the stations, the underground stations, and this is a tunnel going through, which is the metro in the future we're going through. So this is essential because there's will be a tunnel boring machines that will mine through this elevations of this depth, and you want to know what type of soil you are dealing with, sand or clay at least. So if you go to the details of the boring logs, they will tell you more information like the strength of the soils and the density of soils. So where on the progress on your mine through the ground, those informations were very, very helpful for design. Particularly, in the future, if you have a foundation need to be built, so those informations will be helpful. So these two slides here, I just want to give you an overview on how like the geotechnical practice uh, make use of the geotechnical data. So, but the focus of this lecture will be talk about those SPT and CPT testing in more details. Okay, standard penetrations test, SPT. So the picture here shows you the demonstrate your very like basic concept of the testing method, which you have like a hammer dropping into rod that penetrate into the ground. So you can lift up the hammers and then you let the hammer drops under gravities, and each times the hammer pounds on the the ward go into the ground with advance. So we keep track with like how many pounds or how many like drops it takes to advance certain like interval, 18 inches, and that gives us the correlations on the end values, which is the number of drops to advance 18 inches. So that is the basic concept of SPT testing. It is a very common test worldwide. This is kind of like the very first field testing that we use in geotechnical engineering. So that's why there's extensive database available worldwide. Particularly in the United States, is a very historically is a very very popular field test. And it also allows you to use the split barrel samples techniques to collect soil samples. So pretty much like you're not just like pushing a water into the ground, but you're pushing like a sampler in the ground. And then when you retreat the sampler, you can take out the soil samples and actually do soil classifications there. And we will do the counts the n values to every 2.5 to 5 inch of like a depth intervals. And the drop hammers by standard is 140 pounds. And then we have a fixed drop height of 30 inches. You can collect disturbed samples, and in some occasions, with advanced equipment, you can even collect quote-unquote undisturbed soil samples. And there's another ASTM standard in addition to the standard 11586, and there's another ASTM standards of 4633 just to describe the energy measurements for SPT. So we will talk about this in more details in later slides. And then within like each n values, we would do like a 3 to 4 increments of 6 inches interval. So I mentioned 18 inches previously to account for the n values. So this 18 inches is make up with 3 6 inches interval. And after we make like the 3 each as of 16 intervals, and the last 2 increments of those 18 inches, which means 6, 6, and 6. So the latter to 6 inches, the up to 12 inches, that is your SPTM values. We will come back to this to talk. We have another graph to illustrate better on this SPTN concept, which is quite important for this method. And last but not least, when you get your SPTN values, then we can use this penetrations bocons, which uh, represent, in some way, you represent the resistance or the stiffness of the soil. That's what we want, and we can use those parameters to empirically correlate with the soil properties we need, such as density, soil strength. We learn about that in lecture 1, and drink shear strength for clay, or the friction angle for sand. So we can establish uh, soil parameters based on this SPTN values. And we'll talk more about how to collect those SPTN values. So here is another picture to look at the device. So this is the hammer again, and you have a driving head, and you have the certain drop height to pound on your driven pipe. And eventually, the whole vertical alignment will connect it to your sampler. And we have two different type of sampler, the split pun. So this type of sampler is to collect disturbed soil samples. And there's another kind of sampler, which we call the tube. And this is more advanced, like a techniques, usually more expensive, because this allows you to collect the undisturbed soil samples. Well, be very careful. This is not 100% perfect, but relatively, this is better quality than the disturbed one. So the disturbed ones in general means like there's much more effort on preserving the soil samples that you're collecting. End up like you become um, uh, a better quality that you can conduct advanced strength laboratory tests, for example, triaxial tests on it to get more reliable data. Since you're like a penetrating the ground, so you're disturbing the ground anyway, so nothing is perfectly undisturbed. But there's difference between the disturbed approach and the tube type method to collect undisturbed samples. So if you use at least if you use the tube type of sampler, uh, if the contractor done their job right, which means the samples that we treat is acceptable to conduct advanced triaxial tests to get more precise measurements of the soil strength. So this usually happens on more like a more sophisticated or more like budget allowed project for you to give the money and give the budget and give the effort to get better quality soil strength parameters you needed for your project. But anyways, so this is the a closer look on us. Let me try to use other color here. So this is a closer look on the split pun sampler. So what we have here is the tube, the Shelby tubes are going to the ground. So you have this relative sharp edge over here as the cutter head. And when this, so this is kind of like a little bit like upside, like a bit sideways. So this part here pretty much is this end, and this edge here pretty much is the edge right there. So when this tube or the sampler is pushed by the hammer or the rod connected it go to the hammers, is advanced by the droplet hammers. So the soil will be pushed in this way. So assume this is soils, and then this assembler is pushed advanced to the ground, and you will get all the stress concentrations right there. So that's where the soil disturbance come from. So it's not perfect, but um, at the end of the day, the soils will go into the sampler. And we have three different types of hammer. We have the donut hammers, which is the very old school original one. So pretty much you are dropping 104 pounds of like a donut type of weight to the header, and then go to the water and go to the sampler. And there's like another one come later called a safety hammer, and also there's like a more sophisticated one is the automated hammer, which is hydraulic to power the whole thing. So this picture actually illustrate how an elevation viewed on how the assembler advanced into the ground. So as I mentioned before, you will be when this wort is advanced into the ground, we start counting the number of blows that need to be advanced by every 6 inches. So for example, here is the depth that you want to look at. So every 6 inches, you will monitor how many like a number of blows to advance that interval. For example, like maybe your very first 6 inches, you would take like 5 blows to advance 6 inches, and another 6 blows to advance another 6 inches, and then another 7 blows to advance the last 6 inches. And in order to to represent your SPTN values for the soils here, you will just add up the second last two interval of 6 inches. So your SPTN values will equals to 13. Because why we ignore the very first 6 inches is because we at that point we assume your sampler or the cutter here is still not fully engaged with the soil. So we expect like you have relatively more soil disturbance at the very first 6 inches. So we always we're according to ASTM standards D1386. The number of blows that you get from the first 6 inch, it won't count as your SPTN values. But after that, the second and the third 6 inch interval, the sum of the the blow count will becomes your SPTN values. So we call this the wort error. There will be some corrections later on. We will discuss on how to correct like whatever you get there. We'll talk more about that. But at this point, at least we know what is the SPT blow counts values. So the next couple pages kind of like illustrate like how things work. So your first increments, we don't count on that. We only count the second and third 6 inches increments. So we mentioned about this the split spoon assembler. So this is a split spoon assembler. You can collect. So this split spoon assembler, you can retreat back to the ground surface, and then like after you open it, then you will get the soil samples. And the soil samples, make sure we need to mark and log it like properly instead of like what type of uh, sampling techniques you're using, the numbers, the depth, and recovery soils, and also the moisture. If you can do a quick test on site, or just like describe it by visualizations, and make sure everything will be documented well. and you will paste it into a container, and the container will be stored in a wood or cardboard box. So the point here say want to mention is like uh, everything we do, we need to put effort on all the details, documentations, and also effort need to be done to minimize any kind of soil disturbance, including like loss of moisture, uh, transportations, and also proper labeling. Everything need to put effort on that, such that like information won't be lost or won't be confused, being confused later. And at the end of the day, like the clients or the project spend so much money to mobilize a rig to site and pay for engineers on site to do all this work. You want the job to be done like properly. And for the soils, make sure like effort is given um, to minimize any possible disturbance, including loss of moisture. So everything need to be like sealed to minimize the moisture loss, and also make sure like everything is packed well, protected well, and also try to minimize any kind of vibrations you may have. So this SPTN method actually is not very ideal in a sense that there's many effects that can cause a disturbance. Um, and it is the very first type of field method that we developed. Back to the old days, we don't have very fancy technology instead of equipments, and also uh, data interpretations method or computational method. So this type of SPT blow counts, dropping hammers, and then you kind of get an index correlated to the resistance, soil resistance, which is quite simple to implement, but it comes with a price that um, it can have many like other effects, influence your end values. For example, if the borehole is not clean enough, then your SPT may not be accurate, and you may like have a false end values that become too large. And also make sure like the head is adequate, and also we need to make sure like the measure of the drops is proper, because each drop, especially for the old school one, the donut type of hammer, the 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 accuracy of the SPTM values highly depends on you have a constant drop height. So you need to make sure the contractor who like manually rise up the hammer every time you do it, you need to be kind of a constant drop height. So if they don't have if uh, a constant drop height, someone try to cut the corner, like then they drop the hammer with a reduced drop height, end up then you don't have a correct amount of compaction of like compaction effort, then you will give you like SPTM value that may be too large than it really is. So everything need to be very careful. The hammer weight may not be accurate. With the hammer like being abused, used so many times, like there's wear down on the hammer, so it may not be accurate anymore. Um, so make sure everything is like aligned well. Otherwise, um, the will come back to have inefficient hammer energy, um, and also make sure everything is done properly. Make sure like assembler is driven like correct positions, um, and the someone like go on the field, make sure when they count on the number of blows, make sure it's just the record is right. Otherwise, like there will be like a human error there. Make sure the sampler need to be standardized, and so forth and so forth. So there's many things like this SPT can be go on because it depends on a lot of human factors. But yet this method was very popular in the past. Uh, we are still using it nowadays, And especially when you practice as a geotech engineers, many times like you need to go back to old data reports because, like for example, your project site, next to your project site, there was like a historical buildings that is 50 years ago, and with good documentations, you can still recover the geotech data, and very likely back to those days, the type of like field testing you can get this SPT, and then like end up like you make use of the data will be helpful for the project. So understanding all of this will be essential as a geotechnical engineer. So we talk about the correlations right there. So end up like what we have is the n values, and the SPT n values will help us to find all those parameters that will be useful for our foundation design. So this n values is powerful in a sense that it can correlate with many other soil properties because many of the soil properties is related to the resistance or the stiffness of the soil, which can be captured by the penetrations resistance that from dropping a hammer. So some parameters we focus on the semester, like the undrained shear strain, the unit weight of the soils, and the friction angles. We keep talk about this in 366, and now this class is for us to use them to design our foundations. So we talk more in the later slides to uh, further elaborate how to convert the SPT and values to the soil strength. Okay, so this slide show you the two different sampling methods, the disturbed one and also the undisturbed method. So the disturbed one, we use what we call the split plume sampler, which you can see here. Okay, so this slide shows you the two sampling method, the disturbed one versus the undisturbed sampling method. So the disturbed samples, what we use is the split uh, spoon sampler. So pretty much like you don't care about the quality of the intact sample. So what we want, the main purpose is for soil classifications or for soil moisture measurements, or like and also the classifications can either be done on site, where at the spot after you retrieve the soil samples, or you ship back the soil samples for lab to do more details index property tests like allele limits or soil classifications. So we call these double samples because eventually you can break down the soil particles. Versus the other one is the undisturbed samples. We use the different types of tubes. So you see the different size and also the thickness of the tubes depends on the project and also depends on the soil types. You select one that for your project. We usually call those to be the thin wall Shelby tubes, which you preserve, so you cannot split up the tubes and then collect the soil samples. Pretty much like if you want to uh, get a soil samples out of it, you need to use a hydraulic jack to push up the soil samples, or like even the highest qualities one is you will cut uh, the Sharpie tubes right at the interval, at the elevations that you want. And then after you cut the tubes, you push up the soil samples. The soil samples will still be intact and in the cylinder form. And then you trim the soil samples down to a triaxial size, which is with a diameter of 2.8 inches. So those two tubes are typically larger than 2.8 inches. So after you collect soil samples, you can trim it to the size you want. you need for triaxial testing, and then you can do a triaxial test, get the stress strain curve from the soil. So this is the undisturbed soil samples. Bear in mind, um, even though we call it to be undisturbed soil samples, all the soil we treat from the ground and then go through all the transportations, and like you push out the soils, and at the end of the day you will be disturbed at some degree. And how much is disturbance? It depends on how careful from the contractor to the lab technicians, and also the storage and everything's matter. But in general, we call it undisturbed because this, when you compare it to the disturbed sampling method, this one, have some promising on reserving some of the fabrics, and also the nature, also the original soil's responses or soil behavior or soil structure uh, of the material you get from the ground. So corrections for SPT n values. So now, uh, when we do our SPT blow counts, this is what we measure. So this is the raw data, the raw SPTN that you collect from the field. But since there's like so many different types of SPT rigs, and also like throughout the history of practicing SPT, there's different times like the equipments may be a little bit different. So through times, through generations, the efficiency of the SPT, because of the we get better machines and the technology advance. So all this thing will be changing, and yet we just use one parameters to represent the soil resistance. So we need those. We need like a procedure to correct the SPTN values, such that like when we see SPTN values, somehow you have the consistency to represent all the different type of equipments available, and also uh, through times or through history, we take care of the difference or the advancements of machines or technology. So that's why we need all these corrections parameters. And after we correct it uh, um, for those parameters, so those parameters like the C sub E, C sub B, C sub S, and C sub R. So those pretty much are for equipment's corrections. And then we get the corrected SPT. So this is the N60 stand for the corrected M values corresponding to 60% energy efficiency. So what are those parameters? So first of all, C sub E is correct for the energy ratio. So different types of hammer, we mentioned before, the donuts and the safety, and also the automatic hammer. It has difference of energy efficiency. So the very like original one, the old school one is the donut hammers. As you can envision, it has the lowest efficiency. And you see a range over there from zero point 0.5 to 1. So you embed a lot of uncertainty. So if you become an engineer, then like you need to make a call. So when you're practicing geotech, you need to make the call. Should you use 0.5 or you should use 1.0? So you need to make that judgment. And the more informations you have, the better helps you. So you can send you can each drill rigs they may come with efficiency report, and there's a ASTM standard over there to describe like what kind of efficiency ratio user use. So if everything done follow through ASTM standard 4633, the contractor may provide you a report, and then that's able to tell you what type of efficiency it is. And the more advanced one, you have a high efficiency. And the second correction factor C sub B is the borehole diameters. So if the penetrations borehole is larger, then you have a relatively higher corrections factors. So this gives you all these numbers right there. And the next one is the sampling method, C sub S. So if you are using a standard sampler, then uh, the baseline corrections is just 1.0. But if you have a non-standard sampler, then depends on sampler, then you may need to change the number. And also the word length. So we mentioned about previously, there's a word connecting. There's a dual word right there connecting. Oops. Your hammers to the header and then also to the sampler. So this word length right there also affects your correction factors because again, imagine it's like, it's not just like kind of like a Cal State area, or not even just like California, or even not just like United States practicing this SPT is worldwide. So different country or different like companies or different type of equipments, they may have a little bit difference of um, a setup. Then based on the walk length, we also need to correct for the factors. So there's the C sub R right there. So hopefully, like, if you have a contractor work with you, and then like they should provide you the dual rig should provide you all this informations. But if you need somehow like when you're working as engineers and you need to go back to some historical data to help your project, and some of the informations may be missing, and then at that times like you need to make judgments, what type of assumptions you assume, and then move on. Well, likely that may happen to your homework assignments or your semester project, which will require you to use some SPT data for a foundation design. But like, at that point, like if any like anything not clear for this class, feel free to ask me, and then based on the information that we have, maybe we can look together. So after we correct everything to from SPT-N to N60, there's another one more corrections typically like we need to do is to change the SPT SN60 to N160. So what is N160? N160 is the normalized N60 to 1 atmosphere over the overburden pressure. So it's not just because of the equipments, the different type of equipments we want to be corrected, but also like a different overburden stress. We also want to standardize it because through like a borehole at different depth, you will have a different pressure. Just remember when you calculate effective stress, vertical effective stress, which just depends on the unit weight of soils and also depends on the depth. So the higher you go down, and then the higher pressure it expects. And so at different like locations, that you may have a different resistance, which means different like N60 uh, N60 values. And this N160 allows you to standardize your N60 by multiplying this factor C sub n, and this C sub n pretty much is the atmospheric pressure, 1 atm, divided by the vertical effective stress. So if you have this locations, you have a vertical effective stress. If you have another locations, then you have different vertical effective stress. And this C sub n right there will help you to take care of the different locations, end up like everything becomes standardized to N160. And this is to power n, and n is for soil type. So n equal 1 for clay, and 0.5 to 0.6 for sand. So here is an examples of the of our Boeing logs, and on this Boeing logs, they are capturing the SPT flow counts, and it's over here is like a volts per foot, so it's per 12 inch. So from here, and then I know that um, this is has already been take out the first 6 inch of increments. So remember, like we talk when we talk about this, how to record the SPDN values. We only consider the last two 6 inch interval, which is 1 foot. So you may see other Boeing logs where like they may be homework. You will see sometimes the SPTN values is given maybe something like this, which means like this is the first 6 inch, this is the second 6 inch, and this is the last 6 inch, and this make up with at 1 foot. And SPTN only take account to the last two 6 inch increments, so SPT should be 13 right there. So in this Boeing logs, it tells you is already tells you is from a foot. So which means those are ready to go SPT vol values, SPT vol flow counts at different depth. So you got like a one measurements right there, n equals to 28, and also at 10 feet down, and also n equals 20, about 30. SPT n equals to 36 at a depth of 10 feet. So pretty much this gives you the SPT n values, and you will need the corrections to correct your SPT n to n60, and you may also need to convert the n60 by multiplying c sub n to get the n160. So we'll come back to this point log to our discuss exercise to show you how to do the corrections from SPTN to N160. And remember, changing SPTN to N60, you need many informations like hammer energy and also like the borehole diameters, so forth and so on. So this may give you some hints on how to get those C sub E, C sub B, C sub S, and C sub R. So if this is what you need to find out, if you give historical data, but if you work on a new project, that you can hire your own contractor to do the SPTN values for you, then very likely you can obtain those informations from the contractor, because they need to provide everything uh, from the equipments they're using. Okay, we'll come back to this to talk more about the corrections. So this gives you like a sense on how those n values. So this is only called n. So this is the raw data, not the corrected ones. How a different range of it, and what type of a soil properties you can expect. So this is CPT, cone tip resistance. But we'll come back. This is the second type of field procedure we'll cover in this lecture. So we'll come back to this Q sub T later. But this n value right there, it tells you the ballparks. It can correlate with the density. So from a very loose material for sand, so you have a relatively lower total density, to very dense material, you will have a much higher density. Same as the friction angle, from very a loose to very dense, very weak to very strong. Same as the clay. So the clay can also give you all this SPT uh, values, how we correlate with the density, from very soft to very hard. So here give you a more correlations with the soil strength parameters, which is essential for our foundation design. So we use friction angles to describe the strength or cohesionless soil, and different author they have different or different. This is a different academic publications or from different academic institutions. They may have different correlations, and as you can tell, they would correlate with a specific type of n value, not necessarily the raw data. In many cases, not the uh, the raw one. Very likely is the M160. So make sure, like, because again, like, all those equations there were established with like a database with data from all over the world, from, like, across all the time history from a couple of decades. So they have a database and they try to build up like correlations. So in order to compare apple to apples, or SPTN that, like, once obtained, they need to standardize it by changing it to SPTN to something like M160, and then end up, like, they have all these correlations. So as you can tell, like, this the highly depends on the database, and also the, database means, like, could be data from United States, or data from Japan's, or data from um, Europe. So depends on where people get the data, and then they may have different correlations. That's one point. And also different type of equipments may happens a little, may change a little bit still. So that's why you see this a great deal of variations right there. So if you have SPTN values for 15, you could have friction angles like as low as 30 to something like 37. So the lower bound, upper bound based on different equations. So in the future, as engineers, you need to make the call, make the judgments, which correlations that we're using, and then which friction angles that you may have at the end of the day. So it depends on the correlations, and then you may have a different friction angles. So this is for sand, and for clay is very tricky because back to the old days, like someone like Tosagi and someone like Hara at all. So Tosagi is very famous. He's kind of like the father of geotechnical engineers. So he make a simple correlations on how the undrained shear strength of clay, which is the cohesive materials related to the N60 right there. It's very simple correlations. But he put a notes on his like publications saying like uh, those correlations you need to use by cautions, especially for clay materials, because it's not reliable uh, for correlating SPT with clay value or with clay strength, because too much disturbance has been caused by using the SPT. So we end up like the SPT uh, correlations is not very reliable. But like if engineers, if like for your projects, there's none of the available like informations available. It's too expensive for you to collect soil samples back to the lab to do a test, and SPT is the only information that you have. Then you may want to just use those correlations with a lot of cares right there. Be very careful on using this, and then understanding this is not reliable, but give you a ballpark values to get started. So maybe at that point you want to use it. So the most uh, thing over here is to be careful on all those like correlations. Correlations is correlations. Even though for the sand, you can see huge variations right there. So be very careful on what you're using. And for practice, for the best practice for getting the strength of a clay materials is through lab testing. So you need to obtain the undisturbed soil samples, clay samples, ship it back to the lab, and then like conduct a tri-field test to get the soil strength. That's a more appropriate way to get the soil strength for clay materials. So after we talk about this correlations, it also good times to go back to this class examples. So this point logs give us all those SPTN values there, and those SPTN values will help us to obtain soil properties that we may need. So, for example, this spreadsheet I also make available on Canfax. Kind of walk you through how to from the SPTN values at the depth that it is. So, for example, again, like at the depth of 205 feet, we got n value of 24. So it's exactly same as here. So at like a depth of 2.5 feet right here, we got n value of 24. At a depth of about 5 feet, we got a 28 of SPTN. So depth of 28, we got 28 n value, so forth and so on. So this is the raw data from the field, and then next we will correct the n values to n60 by those factors. So the factors right there is from the hints from this chart. So for example, here tells you this pretty much like tells you the hammer data is a 140 pounds and 30-inch drops. So this tell me pretty much a donut type of a hammer. And for donut type of hammers, uh, we know the correction factors is from 0.5 to 1.0. And 0.6 is a reasonable numbers to use. So that's why I pick 0.6 over here. So your engineers, you will make the choice, and through experience, you will know you feel more comfortable picking a number to use. Also, CB is the borehole diameters based on the size of the boreholes. Hopefully, we have that information right there. So we know this is 8 inches outside diameters, and with this information, we can pick the C sub B. And this is a standard sampler being used, or so we use a C sub S equal 1, or actually here may not give you the enough information, so you need to make some assumptions. Sometimes if you don't have information, you want to be a little bit conservative. So I pick 1 for the C sub S, and also here hopefully they talk about the word length. If no, then also we need to make the assumptions for the word length corrections for the C sub R. And then this N60 will be the multiplications of the SPTN with all those correction factors. And for each intervals, the boring logs also tells you what type of materials is it. Is it sand or clay? So we can put on the soil classifications based on the soil descriptions, and from there we can assume the unit weight of the soil with this table here. So you know the SPTN, and you know like whether sand or clay, and then based on SPTN, then we can assume the unit weight. So we will need this unit weight later on for our N160 corrections. And you know the unit weight, and you can calculate the vertical stress, and also you can calculate the pore pressure. And if you have encountered water tables in your boring logs, in your boreholes, then you should receive the information right there to talk about water table. So here, say the groundwater table is as 22 feet below the ground surface. So you know that the groundwater tables is greater than 42 feet, and the information we have is only up to 35. So you know that there's no groundwater that was an encounter for this borehole up to the depth of 35. So you know the water pressure is 0. So you can calculate effective stress. So after you calculate effective stress, then you can calculate the C sub n. So the C sub n is given by these equations. So C sub n pretty much is the atmospheric pressure, 180 amps divided by the vertical stress, just you calculate. So a constant divided by the vertical effective stress, and the n values will depends on whether it's clay or sand. And I am a little bit at the conservative side, so I use a zero point 0.5 for the sand and 1 for the clay. So from there, then I can calculate C sub n. So sand, then I will use like a zero point 0.5, and if this is clay, actually I should use 1 right there. So for sand, this is a SP sand, so it's 0 0.5. So after you calculate the C sub n, you can calculate the vertical, the N160. N160 will be equals N60 times the C sub n. So again, I will upload this spreadsheet on Canvax. So if you have questions, you can go back to this like examples. And if you need further help, please come to my office hour. And after we know the N160, we can calculate the friction angles with the equations or the correlations equations that describe it on this table. So I try to use the Corway and Mayen. I use the Mayen and Law 2001 and also the JRA correlation. So I tried the three. So you see some variations right there. So all these equations here pretty much is described in this table. So I find the friction angle for the sand originally from the SPT and also try to estimate. You need to use this with a lot of care. And at the end of the day, when I practice like those and drink real drinks for SPT pretty much is just will be on my calculation paper. I just want to give an ideas what type of soils or what type of strength I'm getting, and with understanding that this is not reliable. And if I have the money for the budget, then I will collect soil samples to do a compaction test or triaxial test in the lab to get a more reliable and shear strength for clay rather than trusting those SPT and correlations. And also the other fact I may have forgot to mention is when we collect undisturbed soil samples, we can only collect clay samples. For sand, it's cohesionless, so there's a lack of cohesion to holding the sand particles together. So that's the reasons why we cannot recover any sand samples. But we need to rely on the field testing, something like SPT or CPT, that we can get the friction angle out of it. Otherwise, like we cannot collect undisturbed samples. You can collect like a disturbed sand samples, but you need to reconstitute the sand samples with the density you want in the lab. But if you go that way, then you lose all the fabrics on all the soil sand structure or the soil structure that you may have in the field. So um, these examples walk you through from the SPT n values to corrected N60. So you from N to corrected N60 and further to the corrected N160. And from there, we talk about how to obtain the soil parameters that we may want, including also the new age. Some many times is very useful too. Okay, so the other type of field testing method is the CPT, cone penetration test. So overall, this is a more sophisticated test that developed and also being popular in the last like 2 decades. So you come with an idea that you'll be instead of using a hammer pounding like a penetrator or sampler into the ground, but this will be through hydraulic power, you will push a cone into the ground continuously. So you get rid of the or you advance the idea of having a descripted like a point of measurements, because like SPT, pretty much you are making measurements at every 5 feet or every like you're limited by a descriptive points. But here, you continuously push a cone into the ground, and then you will have kind of like a continuous profile on the soil resistance. And when we talk about CPT, include like a different size of cone. So you see the picture here. You can have mini cones uh, up to like a relatively large diameters of CPT cone. And the cone here, you can have more sophisticated measurements. Um, you measuring the tip resistance at this point. So this is the tip resistance. So you have the directly kind of correlate with the stiffness of the ground, and also at the side you can measure the side frictions. You have also the size resistance that you are measuring. So the symbol for that is Q sub C, typically for the tip resistance, and F sub S is the side frictions. And that's to STM standard reference to this test. I should make it I should have make it available on Canvax, which is D3441 and also D5778. There are many like good reference out there for CPT testing, um, and there's two good one. First is by Nune, Power, and Robertson's 1997, which is kind of like a book talk about CPT testing, and also Mayan 2007, which is free. Freely available online, is also a good reference about the documentation of CPT. And I also have upload a lecture by Robertson. So Robertson is very famous in the CPT testing. He pretty much is the one that like developed most of the technology in this field. He used to be a professor in Canada, but now he's a practicing engineer, actually working in Southern California. So he has a lecture, kind of like a work an award lecture given on this topic, and I will make it available on Canvax. You'll be quite in depth and quite advanced, but you also get a very good introductions of CPT. So this is another picture on showing you how CPT work, and usually like the CPT equipment is embedded with a truck. So you will see like one of the limitations of the CPT now is that it cannot go too deep, because uh, depends on the size of the truck. The pressure or the resistance cannot exceed the weight of the truck, because it's kind of like action and reactions, Newton's law, that you're pushing a cone into the ground, and then like the reaction force will be balanced by the weight of the truck. So when does cone like advance into the ground? So we are measuring the tip resistance right there, and also the side frictions, or they call this the sleeve frictions that you have. And for more advanced a CPT device, you will have like a pore pressure sensors right there, so you can also measure the water pressure. And on top of that, like even more advanced like a CPT, they call those the seismic CPT, and you may have like even more advanced geophysical parameters. You can measure shear wave velocity as the cone advanced. So um, CPT is still a developing a technology, so there will be like a more and more advancements to come. And there's always a long debate as should you use SPT or should you use CPT. Uh, as a geotax, you should like understand like both advantage and disadvantage of each of the methods. Yes, CPT is more sophisticated. It's more like uh, uh, capable on measuring like more parameters that you may more than more than your need, but like you also need to understand the shortcoming coming with it. So this is a picture of a real picture of a CPT a truck. So this is how it looks like inside the truck. So you see like this is the hydraulic pump right here, and actually this is the CPT cone. So it's pushing down this way. Everything is powered by the hydraulic power, and all this like a watt over here. Also, those are the CPT cone. You keep pushing it, advancing the cone in the ground, and you are running out of the length, and you will connect another one, so forth and so on, until you get to the depth that you want, or like you reach the limit that uh, is bounded by the reach of the truck. So this is how the results look like. Uh, Again, we have a couple measurements. We can measure the tip resistance, and also we can measure the side frictions, so the slip frictions right here. And we with our paw pressure sensors, we can also like record the paw pressure. So at least from the paw pressure, you can tell you start to pick up the water pressure at this depth, so you know the water table. This is quite clear. So the water table for this case, sometimes like the data could be a little bit like messy or a little bit like a noisy, then you may have a hard time to interpret the data. But this one is obvious for the water table. It's at about like a 10-meter deep. So well, this is a continuous measurement. So unlike the descriptive measurements from SPT, actually you can retrieve soil samples and then like to examine or do soil classifications by clearly to say, oh, this is a sand and this is a clay. Uh, but the CPT, you can see all the layering effects here. So pretty much you can tell. Uh, use other color. So this is one type of soils right there. Or maybe like this is within like the first layer, you may be able to find more sub layer. And very clearly, this is another layers with all this like tip resistance and side frictions right there. And here maybe your third layers. Here maybe the fourth one. So CPT will record all this data, and there will be engineering procedure on how to convert like all these measurements into what we want. So what we want, right? We want the soil classifications. So CPT actually can do it without actually retreating any soil samples. And also what we want is those soil parameters like the unit weight uh, and also the string parameters that we need for foundation design. So eventually, what does it mean? There's like soil classifications. Is the functions of those parameters that we are getting, and also like other soil strength parameters. So the Q sub T, the tip resistance, and also the side frictions can give you the parameters you need, like unit weight of soils, soil friction angles, and undrained shear strength. So soil friction for angles for sand and undrained shear strength for clay. So we can do this, and so by how? So this is the Robertson method that try to classify the soils based on the tip resistance and also based on the side frictions. So if you have a combinations of those two, then from this chart, so there's more like a procedure, more like an engineering procedure you need to do before you get to the point that you can use this chart, because like those tip resistance and those frictions, side frictions, they are normalized. So engineering procedure will guide you through how to do the normalizations and through this all these equations right there. So after you have done all this conversions. Then based on the combinations of Q sub T and also F sub R, then you can classify the soil, whether it's sand or clay, so forth and so on. And we will do a class examples together. So also this flow chart over here shows you the procedure, how to change the CPT tip resistance, the raw data, the tip resistance, and also the side frictions into the normalized parameters that you need, and also the index, the CPT index that you need at the end of the day to do the soil classifications there. So in addition to that, the CPT data can also help you to correlate the unit weight of the soils that we need, and also the undrained soil strength. Remember last time when we talked about the SPT, you cannot reliably to find out the undrained shear strength for clay, but this CPD method claim they can. They can like be more reliable to finding the the undrained shear strength of clay, and as also like soil friction angles, because there's correlations to help us to change the tip resistance, the normalized tip resistance, to correlate with the soil friction angles. So it's all capable to do that. We will do examples together. So before we talk about the comparing, like, or talk about the advantage and disadvantage of CPT, let's do a class examples together. This is the class exercise. So you see on this spreadsheet, which is also available on Canfax. The picture here is exactly the same as the one that you is displayed on your lecture notes. So it has the CPT tip resistance, the safe frictions, and also the pore water pressure. The friction ratios is pretty much just between the tip resistance and also the safe frictions. But anyways, um, the first thing I have done on the spreadsheet is manually to read at each layers. So I assume, like, we have first layer here, and then for sure we have a thick soft soils layer here from 10 meters to about 25 meters. So on within each like layers at an interval of 5 meters, try to read off the tip resistance and also the slip frictions. So this is what I read off from the graph. And this is just because of the enamel, so I try to like read off um, selected points for use to how to better to minimize or reduce the number of data, but in real world or in real practice, very likely for homework and also maybe and also for your semester project, I will give you the digital files, which means that you have a continuous measurements that happen maybe every like zero point 0.1 meters. So you have you need to deal with more data, but anyways, like the whole purpose here is to walk you through how to convert those like a few data to resistance and also the stiff frictions to, at the end of the day, you will have the soil classifications and also from this each of the soil parameters we want, the friction angle for sand or the undrained shear strength for clay. And also we want to know the unit weight of the soils too. So first thing, like the unit weight of soils will be a little bit more obvious because remember we have those correlations equations here to convert our side frictions to total unit weight of soils. This case, this formula is normalized by the unit weight of water. So the calculations here is exactly the formula that I have showed here. So with the psi frictions, we can correlate that into the unit weight of the soils. So with the unit weight of the soils, then we can calculate the radical stress, the pore pressure, and also the radial refractive stress. And the next thing is this Robertson procedure help us to uh, find or to convert those CPT raw data into those normalized parameters that we need, which is the normalized T resistance, normalized safe frictions, and also the I sub C parameters. So we need those parameters for us to do our soil classifications. So remember, if you want to use this Robertson chart, so this is from Robertson's 2009, and I have uploaded a paper on CanFax. Um, so with those like normalized tips resistance and also the normalized frictions, then after we find out those values, then we can use this chart to classify our soils, either sand or clay. And if we know sand, then we want to find the friction angles. If it's a clay, then we want to find the undrained shear strength. So with this chart over here, what it tells us is first, the procedure is to assume the stress exponents n equals 1.0. Then we will calculate the Q sub L, F sub C, and I sub C based on those equations. So first we assume n equal 1, then we can do those calculations. And this n values will be useful right here, because you need to use the C sub n to calculate the normalized tip resistance. So first, pretty much like we follow these equations, will be same as my calculations right here, with this n parameters equals to 1 at the beginning. So I calculate the capital 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 Q's here, and then like I also calculate psi frictions. And after I know these two terms, then I can calculate this I sub C parameters based on these equations. So this is exactly what I've done right there. So after I calculate those three parameters, then like I can go back, because now I know I sub C. I can plug it back to these equations to calculate this n values. Remember, like we assume n equal 1 at the beginning. Now we calculate it. So now I have my n values. So this is my first iterations. And the second iterations is now I have updated n. Then I will repeat the procedure to calculate the normalized tip resistance, and also I know the slip frictions. So with those two, I can calculate the I sub C. So I have an updated I sub C. So with this updated I sub C, I plug back these equations, then I can calculate my second iteration's n values again. So this procedure tells us we need to keep iterate until the difference between the n is less than 0.01. So I can check my difference between the n between my second and first iterations, and until the upon that the n values is less than the difference between iterations is less than 0.01, and I have some calculation, some like a numbers right there is greater than that, which means like I need to iterate one more times. So my third iterations, I will make use of the n values that I calculate from the previous iterations, and with the updated normalized T resistance, then I can calculate the I sub C. And with the I sub C, I can calculate the n values according to these equations again. And the difference between the n, this time I check between the third and second iterations, and all of them is smaller than 0.01. So which means like, we finished like our iterations, which means we got to a tolerance is good enough to to be finished. So the Q sub n will be based on my final n values, and I will calculate that one more times. So I think I catch a typo here. Here should be multiplied. So with all this number, then I can know the Q sub QTN and also the F sub R. And if I go back to those this chart, so I know the Q and know the F, the combinations will be from this Robertson chart will tell us whether this like a sand or clay material. If this is a sand material, then I will calculate friction angles according to the correlations given here, which is this correlations. And if this is a clay material, then I can calculate the unduring shear strength based on these equations. So this is how I find out my. All right, last but not least, I want to make some comments on the advantage and disadvantage of CPT. So the good thing about CPT is it is fast and you can provide continuous profilings. It's relatively cheap. Um, uh, it depends on the locations and also the availability of the contractor. But the overall CPT concept can save time because this is a continuous like a profilings. It can be get done quick. And another very good thing about it is the results that we have is not operator dependence. Unlike SPT, where you need to depend the contractor each times to do their job properly, make sure like they have um, a constant job height of the hammer, and there's like no way for you to control it at a perfect sense. But like a CPT, you will be done by the pushing down the cone by the hydraulic machine, so there's less dependence on the operator. And the other thing is uh, you need more sophisticated like a sensors, so give you more theoretical bias in the interpretations. And also, it has proved in the past that you work well for soft soils. The disadvantage of CPT is first, since you have those like sophisticated like equipments, so the capital investments will be expensive. Also, we need a skilled operator to run the test, but not only like to run the test, but also you need someone who really knows about uh, the testing and to interpret the data. I know some folks in geotechnical engineering, pretty much they spend their whole career on focusing on this, so they make themselves to become a CPT expert. So since you have more electronics to deal with, so the noise, the calibrations, and the drift from the electrical device, those matter. Is you need very good technicians to help you to fix those issues. One huge disadvantage of CPT is you cannot collect soil samples. So, which may hurt you in classifications, because if you go to the Robertson chart, it may not give you very detailed classifications, as you can collect the soil samples, ship it back to the lab to run adequate tests. On CPT cannot do that. And because of the size of the CPT and also the limit on the loading capacity, it's not suitable for gravels or other like even like boulder deposit. Well, neither than SPT can do it, but this become more problematic for CPT. So comparing like CPT to other testing method, where we focus on the center penetration test, because we covered this two tests in this class. So
Comparing the two, SPT is more simple and um, to the point that like CPT has an advantage that like being can it can be done continuously. Both of them are empirical correlated for obtaining solve parameters, and both of them cannot handle gravels. And another key difference is whether like whether they are available using practice. So SPT is the one that we have been using for a long time. We have long histories on that, so you won't be surprised that the availability of SPT is better than CPT. So CPT you required uh, a very specialized like a contractor to do it, but uh, CPT has become more and more popular. So down the road, I won't be surprised to learn that actually CPT is as commonly available as the SPT. But from a historical stand of points, there are a lot more SPT data out there than CPT. So potential for future developments, like there's still a lot of like a room for improvement for the and also for developments for the CPT. So I also like download some table from the textbook. I borrow from the textbook. So those give you an idea on the uncertainty of soil properties measured in the laboratory testing. So you can tell like from the parameter we need, from the density to the string parameters, the COV. So this is coefficients of variance, which is defined by the standard deviations derived by the mean. So the higher this number means the greater uncertainty. So you can tell, like, solid properties, we have a lot of spatial variety. So you always come with uncertainty. So if we do it in the lab, different parameters, we have different uncertainty. The highest one is the undrained shear strength of the clay. You have the highest uncertainty. And same as like other like parameters, like those Albert limits and the consolidations parameters. We also have huge uncertainties on that. How about field measurements? So when we compare the CPT and the SPT, in fact, the CPT is giving you like a little bit better results because you have a lower COV values in terms of the uncertainty, while the SPT mean to be like almost the highest one among the available field testing. So this is a picture showing you like to answer the question, this how much field investigations you need. So if you look at this graph, there's like a sweet spot over here. We care about the total cost of the project, and which tells you if you have. So if you look at this like curve right here, which means at the beginning, if you don't have much uh, investigations, which means like you don't have much field tests, CPT, SPT, or you don't have laboratory tests, you are bearing with high uncertainty on your soil properties. So either you need to have a very huge effective safety for design, or you suffer from any calculations or uh, estimations of the soil properties. For example, you underestimate the soil strength parameters, end up the structure collapse, so it becomes very expensive to fix the projects. Or like you don't have the numbers, so you go the other extreme, so you be super conservative on your soil strength, which means at the end of the day, you need to have much larger foundations, much more than enough to encounter the uncertainty. So the cost of the project will be expensive. But at some point, uh, the cost will be reduced as the uncertainty reduce. But at some point, you have the sweet spot, which means like the more data that comes in, you already know what you need to know, or what you already know what you can know. So the extra information is not helping. So end up you will be just increase the cost by adding the amount of money you put in for these the soil investigations. So this is a very good picture just to demonstrate you the concept of you need just enough uh, uh, money to invest on geotechnical investigations, and the definitions on the just enough, and also how much is enough, that will be highly depends on what you're doing, and also through your geotech career. After you develop have more experience, then you can answer the questions better. So these two tables over here also give you an idea on how much like boreholes you need. So boreholes means like the SPT and CPT. So with the subsurface conditions of three different kinds, like a very bad or like very high quality, which means like you pretty much is quite homogeneous, versus you have a lot of erratic like soil profiles, like so the geology is so complex. You have all this like random sand pockets, or this like a random clay thin layers out there. You want to capture them, so you may have much less spacing between each of the borings. But if you have very homogeneous site, then you may like have less boreholes, or less CPT or SPT that you need. And how deep you need to go down, and also they give you uh, rough guidelines over there. So I borrowed these two tables from the textbook. So those are just some general rules, rule of thumb to get you started. Eventually, how to set up your investigation program, how much borehole you need, and how deep you need to go to, and should you use SPT or CPT. That will be, highly depends on the projects. And uh, as your career advance, hopefully you will have better answer for those questions. And final questions: SPTs or CPT? And the common practice now is actually, uh, if you can, uh, is it's better to include both. So we understand CPT is cheaper and quicker, but SPT has some advantage that CPT cannot replace, which is able to collect soil samples. So if the budget allows, the good practice now maybe is like you have uh, every 2 or 3 CPT to be done, and in some very important locations, for example, like you have a high-rise building, so right at the center of the high-rise buildings, maybe you want to have both SPT and CPT if budget allowed. Or if you cannot, maybe at least you want to have the SPT such that you can collect soil samples for that particular locations, and surrounding your SPT, or like the next locations, you may want to have a CPT. So SPT and CPT informations can complement with each other.